Good evening, everyone. Oh, it's a bit loud. Hi. It is our great pleasure to welcome you all here tonight. Thank you very much for joining us. My name is Anita Gaidetsky. I work with the American Meteorological Society, the AMS, which is headquartered here in Boston, although its professional members can be found throughout the whole of the US. I am delighted that we are finally able to host the second of our annual speaker events, only 2 years later than originally planned. This event on the topic of hurricanes was scheduled to take place in April 2020, but as we all know, world events interfered. However, better late than never. We're excited to finally be able to get together again, both in person and remotely. Thank you to all of you who are joining us online, both nationally and internationally. This speaker series was originally created back in 2019 to coincide with the 100-year anniversary of the founding of the AMS. It was created with the purpose of sharing the wealth of knowledge and expertise in the fields of weather, water, and climate, contained within the thousands of members of the AMS, with the broader public. We held our inaugural event at the Boston Public Library back in October 2019. I do see some of the same faces here tonight, so thank you for coming back. And as for the new faces, we do hope you will be back again at the next event. We have an extraordinary, it's hard to say, we have an extraordinary panel of speakers tonight. I am very grateful that they have taken time out from their busy schedules and traveled long distances to be here, from Atlanta, from Florida, and from New Jersey. I had to travel about half a mile or so to get here. But of course, this had no bearing whatsoever on the choice of this excellent and high-tech venue for tonight. We have much to cover this evening. There are a couple of web pages, if I get to the next slide. There are a couple of web pages on the slide here where you can find out more about the speaker series, eyetowardssky.org, the speakers themselves, and the fascinating work that they do, and also more information about the AMS and ways in which you can stay informed, up to date, and involved. You will also have plenty of opportunity to talk to any of us when we move next door for refreshments later. We feel that there is no better time to become more informed about the important scientific facts and data related to weather and climate. I'd like to take just a few moments to introduce you to our moderator for this evening. Dr. Matt Sikowski was instrumental in helping me put together the content of this program we will be presenting to you tonight, and I personally am extremely grateful to him. Dr. Sikowski is a science editor-in-chief at the Weather Channel, where he oversees the scientific content across multiple on-air and digital platforms. He is also part of a production team at the Weather Channel that won an Emmy Award for its immersive mixed reality broadcasts. If you haven't seen any of these, I would highly recommend you do. He is also a producer for Weather Geeks, a weekly podcast that discusses weather, risk communication, and climate policy. He received his PhD in atmospheric science from the University of Wisconsin-Madison, while earning his Bachelor of Science in Meteorology at Florida State University and his Master of Science in Meteorology at the University of Hawaii, Manoa. He worked at the National Hurricane Center in Miami, Florida, and the Honolulu Forecast Office, the Central Pacific Hurricane Center in Honolulu. And to top it all, in August of 2011, he flew aboard a Hurricane Hunter aircraft into the eye of Hurricane Irene. Spoiler alert, there's at least 2 people on the panel tonight that have flown directly into the center of a hurricane, deliberately, all for the sake of science. This may not be on many people's bucket lists, but it most definitely is on mine. So without further ado, it is my pleasure to introduce Dr. Matthew Sitkowski.
Thank you, Anita, so much. And let me extend my welcome and thank you for everyone for joining us this evening here in the room and both online from the American Meteorological Society stream and also the pattern stream as well. I have to admit, Anita, when this date was chosen, November 18th, I never would have imagined that just a week prior we would be dealing with a landfalling hurricane, but that was exactly the case. Last Thursday, Hurricane Nicole made landfall in Vero Beach, Florida. It was the latest hurricane to make landfall on the east coast of the United States, and the second latest hurricane to make landfall in the continental United States. The record, by the way, is Hurricane Kate, back in 1985, made landfall in the Florida Panhandle November 21st. Hopefully we're never having Thanksgiving dinner while we're dealing with a landfalling hurricane. Now, Nicole caused some pretty severe beach erosion on the east coast of Florida. We saw some buildings that collapsed right along the coast. But it was really no match for the devastation and the tragic loss experienced with Hurricane Ian this year. That was sort of our real big Category 4 landfall that really pummeled southwest Florida in September. That hurricane brought tremendous surge, 150-mile-per-hour winds, and double-digit rainfall that left a swath of flooding across much of the state. And it's those hazards, the dangerous storm surge amidst rising seas, the intense winds over warming waters, and this intense rainfall in a warming atmosphere. These hazards, how are they changing as our planet is warming? How do we monitor these hazards and hurricanes to know why these changes are occurring? And then how do we monitor hurricanes and develop a forecast and warn the public every year when they threaten our coastline? We're going to be talking about this and more tonight. I want everybody in the room to leave smarter than when they walked in the door. We're going to have plenty of time for questions, so have them handy for when we do our Q&A later on. And with that, it is my absolute pleasure to introduce our distinguished 3-person panel, along with a 4th storyteller not shown here, and that is scientific data. That is a theme weaves throughout all of our talks tonight, and in general with science. In fact, Dr. Lisa Bucci, for the past decade or so, was a data collector, as Anita mentioned. She was a research scientist at the Hurricane Research Division in Miami, Florida, and flew aboard Hurricane Hunter aircraft to go into the storm, measure the storm's intensity, its structure, and get that information back to the forecasters at the Hurricane Center so they could make a forecast. She is now on the receiving end of that information as the latest hurricane specialist at the National Hurricane Center, the 2nd female to hold that role, by the way. And now she'll take that information and develop the forecast and create the cone that everyone is so familiar with. Dr. Bucci holds a science and engineering degree from the University of Michigan. She has a Master's of Science from Florida State University, and a PhD from the University of Miami. Now, another Florida State alum, that'll be the third one so far here, is Stephanie Abrams. Stephanie Abrams graduated cum laude with a Bachelor's of Science of Meteorology from Florida State University. She also holds a Bachelor's of Science of Geography from the University of Florida.
Go Gators!
An original native. And she puts that degree to use because she has traveled all across the country reporting on every type of weather imaginable to Weather Channel viewers. Blizzards, tornadoes, hurricanes, you name it, Stephanie has taken her passion for the weather and her enthusiasm for educating the public and sharing the forecast with millions of Weather Channel viewers. She is co-host of America's Morning Headquarters, along with Jim Cantori every morning. And she also is joined by Jordan Steele on The Pattern Show, which is the only daily live climate and sustainability show produced every weekday in this country. Stephanie also follows the data when she has the forecast and couches the uncertainty and conveys that to the public and to her viewers so that they can make appropriate decisions every day. As a result of her nearly 2 decades at the Weather Channel, she has become one of the most trusted on-camera meteorologists in the industry. Now, Dr. Gabriel Vecchi might be more comfortable behind a laptop or in a classroom than in front of the camera, but his research often gets the headlines. He is the professor in the Geosciences Department at Princeton University. He is the director of the High Meadows Environmental Institute and the deputy director of the Cooperative Institute for Modeling of the Earth System. It's a NOAA joint partnership with Princeton as well. Dr. Vecchi is a world-class scientist that analyzes, interprets, dissects, and synthesizes data across a wide spectrum of atmospheric phenomena, including tropical cyclones, global weather patterns, droughts, global circulations, a wide variety of topics. His over 200 peer-reviewed articles each tells a story, with data being the narrator. Along the way, has received numerous awards, including the U.S. Presidential Award for Early Career Scientists and Engineers. He holds a PhD in oceanography and a master's in applied mathematics from the University of Washington, and undergrad degree in mathematics from Rutgers University. This is an outstanding panel. It's going to be a fantastic evening. We're going to hear about hurricanes, the real-time forecasting of them. We're going to talk about the trends that we're seeing and why some of them are concerning. And again, we're going to have the question and answer session following the 3 talks, so be prepared. There'll be some microphones in the back of the room. So with that, why don't you please join me in welcoming our first speaker, Dr. Lisa Bucci.
Hi. So what's it like to fly into a hurricane? I thought I'd start off with that question because it's the one I get the most, and I brought some videos with me. So let's get it started. So we're starting off in the eye wall of Hurricane Lane. It was a Category 5 storm off the coast of Hawaii, and I'm just shooting this with my cell phone. So the eye wall is the most turbulent place of the hurricane, and it's where the strongest winds occur. But as you can see in this video, it starts to get lighter and lighter, and that's because we are now entering the eye of the hurricane. And you can see it's a bright sunny day, which is crazy for a storm this strong. You can see that we've come into the eye and you're surrounded by this stadium of clouds that are just swirling around you. And the dynamic environment that you find yourself in, this camera doesn't even do justice because there are clouds just swirling all around you. You look up and it's a blue sky above, and you look down and you can see these waves just crashing beneath you, which is pretty incredible because at this point we're about 6,000 or 7,000 feet in the air. So we drop a couple instruments and take a look around, and then head back out to the other side of the eye wall and continue our mission. And these missions can last up to 10 hours. So let's back up a little bit. So hi, like Matt said, thank you for the great introduction. My name is Lisa Bucci. I'm a hurricane specialist at the National Hurricane Center. But before that, I was a hurricane hunter for NOAA. And this took me into many different storms. My first one was Hurricane Isaac in 2012 that made landfall in Louisiana. And since then, I've flown in notable storms such as Sandy in 2012, Matthew in 2016, and Irma in 2017. And all said and done, I've been in the eye of a hurricane about 70 times, somewhere around there. So why fly into a hurricane? Well, as you can see with satellite data, you get a wealth of information. But a lot of times what you're seeing in these images is what's happening at the top of the atmosphere, at the top of the clouds, and that doesn't necessarily reflect what's happening beneath them. And so the best way to get the most accurate information is to send a plane in and collect that data. So when you see a plane flying into a hurricane, you know that you're going to be getting the most accurate information about that storm at that time. So NOAA every year flies into hurricanes between June and November, which is the Atlantic hurricane season. And we run a field program that happens every year. So every year we get ready to fly. And we're doing this for several different reasons. The first objective that we have is first research. We want basic understanding. We're out there, we have these basic questions, and we're trying to collect information to answer them. And those questions could range anywhere from why does something form when another one doesn't, or why is something quickly intensifying, and how can we know that it's going to happen? So we do research. The second thing is that we do real-time monitoring. And so we sometimes call this nowcasting. And what we're trying to do is get a three-dimensional picture of what's happening in the storm and send it out to the folks on the ground so that they know what the hurricane looks like and have the most accurate picture of what's happening. So we're doing real-time monitoring. And while we have instrumentation on there, we're always testing out new information because there are gaps in our pictures sometimes. So sometimes we want to test out new instruments to see if we can fill in some of those gaps. Next, we're sending all this information into your weather models. So your weather models need a place to begin their forecast. And a lot of times they'll use our data to start off their forecast. So the weather models are also getting this data. And we're doing all of this, all of these objectives kind of lead into one goal, and that's to improve your forecast. So we're flying into storms every year to hopefully improve our forecasts. So we have a couple different types of planes that we fly into hurricanes. And I should note here that NOAA flies into hurricanes, but so does the Air Force. So if you hear about the hurricane hunters, there are two different kinds. There's the Air Force. They typically only fly for the National Hurricane Center, and then there's NOAA. And we do both operational flying and research. So today I'm just going to talk about NOAA's, but sometimes you'll hear about both. So hopefully that clears up some of the confusion. So first we have a jet. We've nicknamed Gonzo, but it's the G4, and it flies high. It flies at about 45,000 feet. And it's there to collect data in the environment around the storm. So there are all these features in the atmosphere that help steer the storm. And what we're interested in is collecting that information so that hopefully we get a better track forecast. Then what the G4 will do is oftentimes fly around the storm, and sometimes it'll even fly around twice. And that's because it's trying to understand how the storm is interacting with the larger environment around it. So we have the G4, it's flying high and around. But we also have the P3s, which we've nicknamed Kermit and Miss Piggy, so you can kind of see a theme in our nicknames. And this is the plane that is like our workhorse of the planes. And here's a little video that I took of getting onto the P3. You can see they put stickers on the side of all the storms that it's been in and all the countries that it's been in. And then you kind of climb up this really steep ramp, and you have to like open up a big door that kind of opens up into this cavern where you're holding anywhere between 15 to 20 different folks on that aircraft. So like I said, it's the workhorse for in-storm measurements. We like to call this our flying laboratory. And the way that it flies through a storm is through a series of passes through the eye, like you saw in the video in the beginning. So it'll fly through the center of the storm, turn downwind, and then turn back in and fly through again. And it just keeps crisscrossing through the storm for as long as we have, fuel. And we're doing this because we're trying to study all the different processes that are happening in this storm that could result in a hurricane forming or a hurricane rapidly intensifying. And it flies anywhere between 1,000 and 25,000 feet, though typically we're flying at about 10,000 feet, so a lot lower than those commercial airliners. So we are in the environment. Finally, we collect observations. So this is actually a video that I took in Hurricane Sam from last year, and you can see there's lightning happening. It was a night flight, and I'm comparing what we're seeing outside to what I'm seeing on the data monitors in front of me. But what we're doing is collecting data as part of our job as a scientist, and we're doing that by dropping instruments off the aircraft. Think about how we release weather balloons from the ground. When we're in the air, we actually can drop instruments off the plane. It'll deploy a chute and then take measurements as it falls down and send it back to us. We also have 3 radars on the aircraft, and these radars can actually give us like a 3-dimensional CAT scan of what's happening with the winds and the rain in the storm. And they also help us with hazard avoidance. There are some places in the storm where we really shouldn't fly, and it helps us kind of avoid those areas. And finally, we have instruments that are attached to the plane. They're measuring data at flight level, and we have instruments that are remotely sensing what's happening beneath us, and it gives us an idea of how strong that storm is. So we're taking all of these measurements, and actually we're quality controlling them before we send them off the plane. We have some automated processes, but because a hurricane is so dynamic, some of those automated processes get rid of good data that it doesn't need to, or it keeps data that's bad. So you have a scientist on board quality controlling the data. We send it out to the world. First, we send it out to the research community. It's available to everyone. If you have an idea that you want to test, you can access this data and figure it out. We share it with our research partners and academics and in governments across the world. We also send it to the weather models, like I said. And now we've always sent it to the National Hurricane Center, but now I'm on the receiving end of this data, so I'm always excited when I know that there's a plane and I'm getting data, because I know it so well, and it makes my job a lot easier. So I'll tell you a little story about putting a new instrument on the plane. This was part of my PhD work, and for it, I put a Doppler wind LiDAR on the plane. We have like standard instrumentation that we put on, but then there are opportunities where we can test out new instruments to fill in some of those gaps, like I said. So my co-advisor, Bob Atlas, was a big champion of this instrument, and it's an instrument that measures the winds in generally clear air with a laser. So he said this would be a really great PhD topic for you, and I agreed. So with him and Sharon Majumdar from the University of Miami, we decided to try and go for it. And he had been trying for 7 years to get this instrument on the plane. Because space in the plane comes at a premium, you can't put all the instruments that you want on board. But we waited, I trained, I learned how to install it, I learned how to operate it, I trained other scientists to use it, and we finally got it on the plane, and we caught a storm. It was Tropical Storm Erica in 2015, and we flew it out of Barbados. And from this video, what you can see is that there are actually quite a bit of clear air, which you maybe wouldn't expect in a tropical storm, but it was a great opportunity for us, and then you get another peek inside of what the cabin is like, and Paul's gonna give you a wave. And so we're really excited. We finally got it on the plane. And we started operating it, and it broke. And so we were like, okay, it's fine. We got another chance. We had several series of flights. So we got it back up into the air, made a couple changes, and it broke again. And it kept doing this flight after flight after flight after flight. What was happening was it was supposed to be scanning. It would start to scan, and then it would just stop and stare in one direction. And at one point, somebody pulled out a big rubber mallet and just hit the scanner. And I just remember thinking, like, oh my gosh, I'm never gonna get a dissertation out of this. Like, can you imagine me getting up in front of my committee and like I'm supposed to be answering these questions of like, does it work in a hurricane? Does it fill a data cap? Is it getting you reliable data? No. I'm not gonna get a dissertation from this. And so while I was like catastrophizing the end of my career, I thankfully had friends and colleagues around me that said, keep trying, keep going, keep troubleshooting. And on the last flight, we were able to figure out that it was a motor that was broken and that we just had to use it in a different way to get data. And we got it, and we were able to write a paper about it. And it gave us just enough justification to put it back on the next year and the next year and the next year, so that finally I was able to get a dissertation out of this instrument. And actually, that video that I showed you at the beginning of Hurricane Lane, we got to fly it into that storm. And we not only found out that it works in early stage storms where there is a lot of clear air, it also works in some of those more mature storms, the Category 5 one. And as an added bonus, this was the first time in 2018, was the first time that NOAA ever had an all-female science crew. And I was lucky enough to be a part of that. So it was a happy ending. So now I'm at the National Hurricane Center, and like I said, I'm on the receiving end of this data, and that is a whole new talk in and of itself, but I can tell you it's an exciting job, and it's an exciting time to be getting this data that we're collecting. And with that, I will turn it over to our next speaker, Stephanie Abrams.
Dr. Bucci, thank you. That was really interesting. What a great story, too. I love that. Anita, thank you so much for having me. I loved meeting you at the Weather Channel. You came to visit. I'm just so happy to be here with you and with all of you and the AMS. It's been a great day and a great weekend so far. All right, so I'm going to pick it up where Dr. Bucci and her colleagues left off, which is they fly through all these hurricanes, and then you literally can access, like she was saying, oh, we send it to researchers. We show their product on air. Like, we will show the planes flying in. We can show you where they're flying in. We can grab their data, and we use this data not only for where we're going to place our crews when we go out to cover these things live, but also just how to inform the public. Because if they see, okay, it's intensifying, and then we're like, okay, it's intensifying, here's the data. The Hurricane Center is actually showing us the data, and we use that in where we're going to, end up, I guess, when all is said and done, because there's certain places we can't end up, and obviously we're going to talk about that. So what I want to do also is talk about the climate aspect of storms, because yes, the climate period is much longer than I'm going to show you. We're just going to look at the last 5 years. And obviously when you're talking climate, you're talking 30 plus years and the whole 9 yards. But this will just give you kind of a good idea of what we are starting to see in the field, where you see a lot of changes happening with these storms, whether there's more of them, they're rapidly intensifying, the rainfall, and just some of the big concerns we have when we're talking about climate. So this is just back, it just is shocking to me. It's like since 2017, this has been 5 years, right? I mean, it's not a long time. And we have had all of these, and all of these storms. Does anyone know what is similar about all of these storms? Any meteorologists out there that know? They're all Cat 4 or Cat 5s, just in the last 5 years, which is kind of shocking. And when you talk about hurricanes, I don't know where everyone is when it comes to how much meteorology you know. So I'm just going to give like a few little refreshers and stuff like that. Is that, you go from Cat 1 to Cat 5. And if it's a Cat 3 or higher, that's considered a major hurricane. And obviously, if it's a 4 or 5, that's a big deal. Ida, Laura, Michael, does anyone remember any of these? I don't know if you experienced any of them. I see a lot of head nodding here. They were all a really big deal because they were just so intense and so big. One of the indicators, and I'm sure Dr. Vecchi will talk about this, is the rapid intensification and how we're seeing more and more of these storms rapidly intensify. And what a rapid intensification is when you have, I'm sorry, I'm so used to being a meteor, I'm like, I need to go point to this here, you know, I'm like awkward, like I need to pick it up and go over there. The maximum sustained winds, they are going to go up by 35 miles per hour in 24 hours. And that's really, really fast. 35 miles an hour in just 24 hours. When you see that happening, everyone's like, oh, geez, you know, our eyes get big. So here's a look again at those 5 storms. And notice, you only need it to go up 35 miles an hour in 24 hours. And look what all these things did. Harvey, Irma, Michael, you go down the list, and you look at Ida, 70 miles an hour in 24 hours. I mean, that's obnoxious, really. Let's just say that. And the thing is about this is that's going from, it went from a Cat 1, I have the numbers here, it went from 80 miles an hour to 150 miles an hour in a matter of 24 hours. So it went from a Cat 1 to a Cat 4, by the way, kind of borderline Cat 5. A Cat 5 is 156 or higher. So it was getting out there. And it did that, by the way, like 30 hours approximately. It's like 29, I think. There's no one in here who's going to knock me for that, right? It was like 30 hours before landfall is when this all was happening. So you have someone maybe that is thinking, oh, they go to bed, oh, it's just going to be a Cat 1. It's all right. And then they wake up, and the next thing you know, it's like, okay, we have a Cat 4, like borderline Cat 5, heading right towards us, which is a totally different story when you're talking about hurricanes. Now, of course, we always advise no matter what the strength, even a tropical storm. I'll tell you, I've been in some strong tropical storms. You always want to obviously be the most protected you can no matter what it is. So, you know, that's one of the reasons that we really have to pay attention to these and get the data that the Hurricane Center is sending in so that we can warn people, and people are paying closer attention. Hurricane Michael also comes to mind because that one was also really intensifying as it was coming ashore. And you can see this, and you'll notice the little mesovortices kind of, you see kind of the wobble in the eye wall here. Like, watch around here, you'll see these little wobbles in there. Those are like really intense winds in the eye wall, essentially. That's a good way to describe it, right? And so this is a look at Michael coming in. Now, for Hurricane Michael, I originally was going to go to Mexico Beach. You can see that here. I'll point it out just in case. Right here, right where the eastern eye wall was. And what we do is we go in our war room at the Weather Channel, and we literally are pulling up like, okay, how hot, what is their elevation there? You can look on Google Earth and look at all the different buildings, like is there anything strong? And I truly was not comfortable, nor was the Weather Channel. By the way, they're like safety first. If you're not comfortable, if they're not comfortable, it's not happening. No one cares. So I was like, there's nothing in Mexico Beach that I feel safe in. Wait till you see the next slide, but we'll get there in a second. So we end up in Port St. Joe. We found this family who, for some reason, had a house. It was built like in Florida on the coast, this huge hill. I don't know what it was or why it was so big. And they had a new build right on top of it. They're like, no, it was built however many years ago. It's all to code, this, that, and the other. Okay, we'll start in Port St. Joe and see what happens from there. So the morning of landfall, we're on air, and we're getting this data, and we're like, oh my gosh, this thing is starting to crank. And here I am on Port St. Joe, right there on the coast, and we see this thing coming in. I'm like, I do not want to ride like a Cat 4, Cat 5, a Cat 3 eye wall out in Port St. Joe. Like, that's crazy. So this shows you a little idea of where I was.
So even though our house behind me is up 24 feet, you see that? We are completely exposed to the ocean. Right there is the ocean, right there is the house. And this thing could come in as a Cat 4,
maybe a Cat 5. So, which of course, it came in technically as a Cat 4, and then they upgraded it to a Cat 5 after the fact. But honestly, like Cat 4, Cat 5, they're both really bad. Like, it doesn't really matter when it comes down to it, right? So we were that close. So that morning, and I was on air with Cantori, and he was like, Abrams, come to me. He was over in Panama City Beach. He was like, just pack up your stuff and let's go. And I have my whole crew. I'm responsible. I'm the meteorologist. I know what's going on. So I said, that's it, guys. I called back to work, and I said, guys, and they're like, yep, we agree, and we all just left because a little wobble one way or another, which these things do, no thank you. So we went over to Panama City Beach, but this is what was left, of course, of Mexico Beach. So a couple of things that you can notice here is, like where our house was in Port St. Joe, it was the ocean, and then you had like A1A, and like our house would be right there. So if we had stayed in Port St. Joe and it wobbled, it could have been a disaster. But notice also how far inland everything went. You know, the waves and the surf, and how just destructive it all can be. It was completely wiped out. So every little square, I mean, you can see people's homes gone, a couple of buildings that are standing, but you know, the thing is that people continue to build on the coast. Can we build, you know, more resilient? And Dr. Vecchi, I know, is going to talk about this and has talked about this, that we have to adapt to these types of things. Can we build stronger? Is it possible? Because these waves and the storms are just so intense, especially right at the coast with less friction, and wipes everyone out. So we ended up in Panama City Beach with Jim. And even over there, where we were in the western eye wall, just for a quick explainer, on the eastern eye wall, the storm is moving forward. And the winds on that side are going in the same direction. So it's like double on the right-hand side. If you ever hear people talk about like, oh, the eastern side, versus the western side, where the winds and the storm is counterclockwise are going this way, but the storm is moving that direction. Obviously, you don't sleep on the western eye wall because it's bad, but that eastern eye wall is like really where it's bad because the storm's moving that way and the winds are moving that way, if you ever hear anyone kind of talk about that. So with all that said, at the Weather Channel, you know, we connect the two and we talk about it. And Dr. Sikowski talked about our show Pattern, shameless plug, Monday through Friday, noon to 1, live. The only live climate talk show and sustainability show. Can't help myself. Our hurricane expert, Dr. Rick Knapp, he was formerly the director of the Hurricane Center and came back to us after that. I asked him kind of like what his biggest concern was, and I was actually a little surprised at his answer. So here's what he had to say about it.
How does climate change affect this forward speed of a storm?
Well, because we are tending to have more high latitude ridging. And so instead of troughs coming in and accelerating storms up the East Coast, they are either recurving more slowly or they're downright stalling. Look at the past several years of storms like Florence and Imelda and Dorian. I mean, these really slow movers at all different intensities. Slow motion makes all of the hazards worse. And that's probably the thing I'm most concerned about, is even if the strengths and numbers of hurricanes are not increasing, and I think the strengths are and the numbers maybe are just a little bit, but I'm more concerned about the water impacts from slower, wetter storms.
Because that's how most people die.
Right, exactly.
Is that surprising? What would you be most scared of? Who would be most scared of the water in a hurricane? Who would be more scared of the wind? Yeah, a lot more people raise their hand, right? But the number one killer when it comes to tropical entities is the water. Now, this slide's a little bit old. It's courtesy of Ken Graham, who used to be the Hurricane Center director a while back. But it's just to point out, like 90% of direct deaths are surge or rain. This goes from 63 to 2012. 90% are from the water, which is shocking statistic. I remember back in Katrina, I mean, you forget all the water pushes up all these rivers, and like way far inland, you have this insane flooding. I mean, the St. John River, after Ian went through, was out of its banks for weeks, literally in flood stage. It was outrageous. And you're talking a river that's inland and people flood inland. So water is the number one killer. This is just 2 years, but also just to show you that inland flooding, this only says 4% storm surge. This was on just obviously a 2-year period. Every storm is different. Sometimes you have more with surge, sometimes more with flooding. But the point being is that water is, you know, the number one killer with all of this. So that is something that we really try to emphasize, because everyone is always obsessed with the winds and the eye wall and where's it going to hit. And yes, that does damage. I'm not taking away from that, but water is huge. Here's another example. This is the record for rainfall from tropical cyclones or remnants. So you're talking hurricanes, you know, any sort of tropical storm that kind of sits and spins. Look at our numbers. These are records for the state. For the state. And this has all happened in the last 5 years. Again, so we're seeing heavier rainfall. And this is a pretty well accepted thing, that these storms are dumping more rain. I mean, it's pretty accepted in the community. Wouldn't you say it's totally accepted? Totally accepted in the community. It's happening. So Harvey, I know now I have like a PhD professor right in front of me. I'm like, Harvey, that's 5 feet. And remember, a 1-story building, this is just, again, very general, is about 10 feet, like in a house. So you're talking about 5 feet. Half of the house is flooded with water. So it's just to emphasize again that the water is such a huge, huge issue. Now, I don't want to discount the winds, because obviously that is a huge problem, and actually more people are affected by the wind. And so it has a huge footprint. This is Laura. Now with Laura, Remember, we're a little bit inland, a couple miles, because you can't be by the coast, obviously, when these storms are coming in. Jim and I were at hotels right next to each other. I was on one side of my hotel, he was on the other side of his. So you'll see him make an appearance in here. And we are at neighboring hotels, and this thing was cranking. And this will just give you a gist of what it's like to be in the eye wall of a Category 4.
It's now 1:15, and it is too dangerous to be out there. Glass has been shattering, and we've tucked ourselves back into a corner so that we will be safe. So I'm going to be quiet and let you hear the sounds of Hurricane Laura.
You know, people mentioned the freight train thing. I think this is what we're talking about. Here's Jim and all his gear.
Oh, yep. Yes, it is going to be close. But right now we're in the eye wall, Steph.
I moved inside. It got too dangerous.
We're now inside the casino, and that is the wind whistling through the building. Do you hear how loud that is? How eerie is that? That is what a Category 4 eye wall sounds like inside a building. Wow! Holy cow!
You can see why we moved inside. It was just way too intense. And by the way, there was power here, which is very rare, but it was a casino. So I've now learned, if you ever want to keep power, they have to legally keep the machines working. I don't know the technicality. Maybe there's a lawyer in here that knows. They can't shut down. I don't know why exactly. So they had to keep the power on. They're like, no matter what, we will have power on. I was like, amazing. So here are some of the winds, just to give you a gist. You know, you're talking Lake Charles, 134 miles an hour. It looks like tornado damage when you're at that strength. I mean, yeah, obviously it's a really strong tornado. And then, of course, we get to Ian here. And remember, all this wind is what kicks up the ocean and causes the surge and causes the waves. This is Mike Seidel. He was with Hurricane Ian right over Sanibel Bridge in Fort Myers. And this is what it looked like from his balcony, where he couldn't get live shots out, but they were taking video. And obviously this isn't even the worst of it, because we can't be where the worst of it is. But this just gives you an idea. I don't know what that noise is, who knows? And don't forget, we're getting, you know, data from the buoys as well that come into us, and we're saying, oh, there's a wave height 30 feet, 40 feet, and you're like, okay, when those wave height starts going up, you know it's a big deal. So that was Ian. And a lot of people would compare when it was coming in, okay, Ian versus Charlie, but we know every system looks different. They have their own thumbprint, as Dr. Sikowski likes to say. And so we just wanted to show you guys a little comparison. Charlie, they were the same speed coming in, but look how much faster Ian was going, 9 miles an hour versus, Charlie was going 22 miles an hour versus Ian at 9. What does that do when they're slower and when they're bigger? They can build up a lot more surge, and obviously it can do a lot of destruction. Charlie was like a buzzsaw, though. This was my first hurricane, was Charlie. I was in Daytona Beach. It was a Category 1, and we had damage over in Daytona Beach, just with these huge things. But surge, of course, was the big deal with Ian, and Charlie got 4, maybe 6 to 7 feet there of Sanibel. But again, remember, same storm, just the size and the speed were different. That's Ian, what we just dealt with. Look at Charlie. So essentially, the core of the strong winds of Charlie could fit inside the eye of Ian. And so Charlie, the wind damage, I remember, was so bad and just absolutely horrific. But quickly, my time's up, so I'm going to get through it as fast as I can. Here's some of your surge numbers. The forecast was up to like 18 feet. And this is all preliminary, but 10 to 15, you know, is what actually happened. And then you have the rainfall. So we try to emphasize also so much on the Weather Channel that these are not just coastal storms. If you live inland, you're going to be affected by this as well. So we really try to remind people, again, with the flooding. And the St. Johns River, you know, by the way, is like, if you look west of Jacksonville, and for a fun fact, it's one of the only rivers in the world that goes north. If you like trivia night, if they ask about rivers that run north in the US, that's one of them. So obviously the slower it goes, the more rain. Charlie, we didn't have this many issues, but the wind in Punta Gorda and everything was terrible. So it's just something that we have to keep looking at. Is we get the data from the hurricanes hunters, it helps us position ourselves, it helps us explain to the viewers what's going to happen. But with the changing climate, are we going to see more of what I just showed you instead of, you know, these happening every couple years? Will it be every year we have these major systems? So that's where I leave you now, and Dr. Vecchi will pick it up and let you know what we do with all that data and how it's all going to play out. Thank you.
All right, well, thank you. I am going to show you the type of data I work with. That tends to be collections of data and also climate model output. And I'll just talk a little bit about the past and the future of tropical cyclones, but taking instead of an event perspective, a multi-decade perspective looking forward and back in time. As we've seen, tropical cyclones and hurricanes are beautiful. This, to me, makes me think of a Rothko, right? It's a gorgeous image. But they're incredibly large and dangerous, as we've seen. The key things to keep in mind are wind, rain, and waves. They leave behind all sorts of destruction, and they have for a very long time. One of the key things about tropical cyclones is you can think of them as a heat engine, where the fuel for the heat engine is the warmth of the ocean water below. And so as the planet warms, one of the concerns is that we're providing these storms with more fuel. We're also changing a little bit about the outflow temperature, the bath, for those of you that think about thermodynamics. So it's a little relatively complicated question, precisely how intensity may change. But we're very confident that we should by making the atmosphere more warm, that is, it can hold more moisture, we should make those storms wetter and also potentially more intense. There's a lot of disagreement and lack of consensus as to what will happen to the frequency of storms. Interestingly, when you think one of the most fundamental things about something is its existence, we can't really pin down. There is no fundamental theory for how many cyclones there should be on our planet, yet we see about 70 hurricanes every year on the world. So that hints that there's a fundamental physical law constraining that. We just don't know what it is, right? And so for those of you that think about, see a young man over there who maybe wants to someday make a change in the world, figuring out why we have 70 hurricanes would be up there, all right? So we have now climate models that allow us to look into the future. These climate models have been refined in their mesh to the point where now we can actually simulate relatively realistic tropical cyclones within a climate model and run it forward in time for 100 years, asking the question, if we continue on the path we are, burning a lot of fossil fuels, loading up the atmosphere with greenhouse gases, what is likely to happen to tropical cyclones? And here is a figure adapted from a paper led by Kiran Bhatia, the former postdoc in our group. And what it shows, I want to just the emotion I want you to leave is when you see something red-orange, that is things getting worse. What it shows in here is the change in number of years on the right, on the left, a number of years in a decade where you will have a category 3, 4, or 5 hurricane anywhere near you, right? Well, around 2.5 degrees, 250 kilometers. That's near the eye wall. Notice that you have an extra 1 or 2 years a decade, 10% to 20% of the years in a decade extra with a major hurricane by the end of the 21st century with major hurricanes. But what I think it gets more interesting, you don't know what these numbers are in the absolute. How many do we get? Well, on the right, we show what the relative change is, how many more years relative to what we've been getting in recent. And what you see is that in many places, it's somewhere around 200 to 500% more, right? 200% more means 3 years instead of 1 in a decade. The black areas, including sort of parts of New Hampshire and Vermont and Maine, are places where in present day we don't have any of these major hurricanes, but the models are indicating that we should perhaps expect them in the coming century. These are places where people haven't adapted to these types of hurricanes because they haven't had to, right? When unusual, unprecedented weather happens is where we find ourselves in a challenge. Now, it's unprecedented, it hasn't happened yet, but we have physics, we have data, we have models, and so we have a foretelling, we have a forewarning. And what do we do with that information? I'm not going to tell you how to live your life, but if you want, I have some suggestions. All right? Now, that is a statement about the future. And predictions are always much more believable when you start seeing the signal in the past. And we've had a century and a half of greenhouse gas increases, very clear. We know that those greenhouse gas increases are driven due to burning fossil fuels. If you look at the isotopic composition of the carbon in the atmosphere, it is very clearly indicative that it is fossil fuel, fossil carbon. It's not sort of biological carbon in our sort of near lithosphere and atmosphere. And we have seen warming of our entire planet over the past century and a half that is very clearly and unambiguously connected to the increasing greenhouse gases. Global warming is real, and it is largely driven by increasing greenhouse gases coming from burning fossil fuels, right? So, given that we've had global warming, and in a future warming, we expect more major hurricanes hitting the U.S., have we seen such an increase over the past century and a half? Well, we have decent data on U.S. landfalling major hurricanes, and it's shown here, the year-by-year numbers in red, and a low-pass filtered, something that focuses on the low-frequency data in black. And I hope you all see that there is no historical trend. We expect something for the future, and we've seen part of the cause of what we expect of the future in the past, the warming and the greenhouse gas increases, but we don't see the increase in the past. What is going on? What has happened in the past that may be different about the future? Or maybe we can blow up our predictions, right? Fingers crossed that we can blow up our predictions, but we can't. I'll let you know the predictions, as far as we can tell, look right. Well, it turns out, shown here is in the blue line, an estimate of the number of major hurricanes across the whole Atlantic. So this includes more storms than just the ones that hit the United States. It's an estimate that has been adjusted to account for the fact that we observe storms differently now than we did 100 years ago. There was exactly and precisely 0 satellites 100 years ago, and there are many now. And so we have to account for that. And there's ways to do it, and it's really cool science to figure out how to do it. How do you ask yourself, what did I not see because I wasn't looking? It's almost a metaphysical question, but it's really cool. It's something that we do a lot. And what you see is in the blue line that the number of major hurricanes in the Atlantic maybe has shown an increase, but more than anything else, what I see there is this big gouge carved out at the end of the record. Sometime around the 1960s, major hurricane activity took a precipitous drop in the Atlantic. Coincident, by the way, with a lot of people moving into the Sun Belt, because air conditioning and energy was available to run the air conditioning. And then, around the 1990s, hurricane activity popped back up. What's behind that? Is that something that is hiding the greenhouse-induced warming impact on major hurricanes? Well, first we can ask, are our climate models that are telling us that we should expect major hurricanes in the future, major hurricane increases in the future, agreeing with the historical hurricane record? And so what I show here is a blue line reproducing that historical record, and the red line is output from the same climate model that I showed you, giving 200%, 500% unprecedented major hurricanes in the US in the future. What it's saying is that the past shouldn't have shown that. The past should have been dominated by is a couple of little wiggles and a big gouge at the end. What is that gouge? This is a question that we've asked, and a number of people have come to the same answer. What happened at the end of the 20th century is, starting at the end of World War II, big industrialization in Europe and North America, driven largely by burning coal, high sulfur coal, led to a buildup of sulfur, sulfates, the thing that gave us acid rain, but also sends sunlight back to space over the Atlantic. The globe warmed over the 20th century, but the Atlantic warmed more slowly between the 60s and the 90s because we had covered it up. We had shielded it with sulfate particles, with pollution. And so we masked the impact of greenhouse gases on hurricanes over the end of the 20th century by polluting with a different substance. And you can see the record of sulfate emissions from Europe. On the left, you see an increase following World War II, and then a big dramatic decrease at the end of the 20th century, largely due to clean air regulations. And when you look at the same climate models that tell us this increase in hurricane activity should happen in the 21st century, when you force them only with greenhouse gases, you get that red line, an increase in intensity over the 20th century. But then when you include the aerosol forcing, in addition to the greenhouse gases, you get the black line, suggesting that the aerosols masked, right, the forcing. And so we have a very sort of bleak or very challenging future predicted by models, while at the same time they're telling us we shouldn't have seen this yet. We're starting now to peel off that veil that hid the effect of warming from us, and we're entering a phase, if you look over here, we're almost back to those pre-industrial sulfates. We are unveiling greenhouse gas effect, all right? Now, the frequency and intensity question is one thing. Rainfall is much more clearly connected to warming, right? Any of you have held a cold beer out on a warm summer day, or a cold glass of milk in a warm summer day? You see that it frosts up on the outside. That's the moisture, the high moisture held by the warm air, frosting on the cold air. There's a very strong dependence between moisture and water. And we saw this in Harvey. Hurricane Harvey, there's a number of studies, Van Oldenburg et al., which I was involved in, Kerry Manuel's study, Michael Wehner's study, all of which showed that the historical global warming made the rainfall from Harvey somewhere between 2 to 3 times more likely. 2 to 3 times more likely. So the odds of Harvey were doubled from global warming. But global warming isn't the only anthropogenic forcing, the only human-induced forcing that affected Harvey's rainfall. So my colleague Wei Zhang led a study that also showed that urbanization, transforming the ground from being a flat grasslands in Houston to being a rough, essentially set of mountains that these hurricane moist winds blew over, got made turbulent, concentrated Harvey's rainfall over Houston. And in addition, when you have paved ground, like I'm looking outside here in the window, that water, when it hits the ground, cannot infiltrate and is more likely to become flood. So the urbanization effect on Harvey's flooding was somewhere around a factor of 20 times. So the combined effect of global warming and urbanization is somewhere around making Harvey somewhere around 60 times more likely, both by global warming and urbanization. And as we continue to urbanize, we need to keep this in mind. Now, another bit to keep in mind is sea level is rising. This is one of my favorite figures in the world because it's 3 independent estimates of sea level. The black line is a radar-based estimate of the height of the ocean from space, and it shows that since the early 90s, sea level around the globe has risen by 80 millimeters, 8 centimeters. What's that? That's 3 inches, right, about. The blue line is using 2 satellites that chase each other around space and measure the gravity of the Earth, so they can measure the mass of water, showing how the mass of the ocean has changed over that time and its effect on sea level. The ocean has gotten more massive. That doesn't mean that it's been bulking up. What it means is that water that used to be on land has flown into the ocean. This is land ice and groundwater pumping going into the ocean. And then the red line is based upon a bunch of thousands of robotic floats that all of us put into the ocean together as a global civilization, right? Have been allowing us to measure the density of the ocean, and we can invert and figure out how the changes in density in the ocean from warming, it expands, have changed the surface height. The purple line is the sum of the red and the blue. Our 3 independent estimates of sea level rise almost perfectly match up. We know why sea level has risen, and it has to do with increasing the mass of the ocean by land ice melt and groundwater pumping, and by expanding the ocean from warming. Now, this is not going to stop. This is expected to continue, and it's not going to be uniform. Some places are predicted to have sea level rise, have been experiencing more rapid sea level rise. So Newport, Rhode Island, has been experiencing sea level rise that is greater than the global average. And a place like Norfolk, Virginia, has experienced even greater sea level rise. And when we look at the 21st century, we expect in some places a mean sea level rise somewhere close to 4 feet or more. There's a little bit of uncertainty here depending on what the West Antarctic ice sheet does and Greenland does. But we know sea level is going to rise, which will make the storm surge, which as we know is one of the most impactful features of a hurricane, more devastating for the same wind speed. So we expect stronger hurricanes from ongoing and future human-caused global warming. The aerosol, the sulfate masking, has hidden this effect from us until recently, right? We've been allowed to wander around this path and build and build and build in dangerous areas without seeing this danger lurking, but we know it's there now, right? And what we call here superclassus clapeyron means that it increases more rapidly than 7% per degree rainfall from tropical cyclones. And urbanization, which is going to be a feature of future human life in a growing degree, is going to impact the conversion of rain to flood. And so we need to factor that in. And ocean warming and ice melting is going to continue to rise sea level. So the same hurricane will be more impactful. Now, these are the predictions about the future. Now, what I want to leave on is a more positive note. This is a prediction, but rather it's a projection. This is what could happen and the severity of what could happen if we continue on the way we are going. But there are technologies presently available that can allow us to decarbonize. Right now, it is cheaper to build a solar plant for the same amount of power than it is to build a coal power plant. Right? We have ways to reduce our footprint on greenhouse gases. Not only that, we have these predictions. We have wonderful scientists. We have a community of communicators that are going out there and giving us information so we can make decisions to adapt. We are not passive in this. We can take action both to adapt to future climate change as well as to mitigate and minimize the future climate change that we have to adapt to. So yes, there's potential challenges forward, but if we want to continue to thrive, we need to take this information, internalize it, share it with our friends, and then do something with it. So with that, I've been well beyond, but thank you very much, and we'll take questions eventually.
Instead, here we'll have our speakers take a seat. Everyone's going to have a microphone, and you, the audience members, have them as well, one on each side of the back of the room here. So I want to encourage everybody to go ahead and get up there.
Don't be shy.
Don't be shy.
I was the kid in class that asked all the questions. Don't be shy. Seriously, ask anything. Don't be embarrassed. I was that guy, so don't be embarrassed.
So yes, here comes our first one.
Let him rip.
So if nobody else has one, I'll just keep on going. So please get online. Yeah. So starting with the hurricane hunting and flying into those hurricanes, I'm curious about if you have this drop-zone technology, right? And they've had those for a while. Then what's to be gained from the plane that couldn't then be gained from a drone that comes in and just drops the drop zones in there? And it's not that, I think it's super cool that you guys are doing it, and I really want to do it also. But why wouldn't you do that?
So we actually have. We have flown drones, a Global Hawk, above the air, above hurricanes, right? We did this first with NASA and then with NOAA. The problem with that drone was that it was really expensive to maintain. So it was a cost issue. But we are still exploring the idea of unmanned vehicles. So we're doing that in several different ways, both from the aircraft. We can release these unmanned drones that actually fly. So it's this small, what we call an SUAS, and it drops out of the aircraft just like a drop zone, like you said, deploys its wings, and then flies around a lot lower in the hurricane where we cannot fly because that's not safe, and collects data in some of the most dangerous parts of the hurricane. We also have, we partner with Saildrone, a company that can pilot these unmanned sailboats into the path of a hurricane and collect data. And maybe you have seen some of those videos of the waves, like in Hurricane Sam. And we also have unmanned vehicles in the ocean that we pilot underneath the hurricane. So we are exploring that idea, and as more funds become available, we continue to explore them. But it's a great question, and yes, we are exploring unmanned vehicles into hurricanes. Yeah. Okay. Should we go over?
Oh, yeah, we'll go ahead. Well, yes, please, over here.
Okay. So I have a question. I spent 20 years as a sovereign credit analyst, and now I write about the economic and financial impacts climate has. And I was particularly curious about the explanation of coal. And I think that's a really cool story, but I also see the dark side of that, and I was wondering if there was, in that being, it could be misused, right? I could see coal, people who like coal say, well, we should pump more of it out into the atmosphere so coal is a protecting force for the planet, and it will protect us from things like that. So I was just wanted to ask, how would you respond to that?
If we only think for half a second, that may be what we suggest. But then we realize the reasons why coal burning was first scrubbed and cleaned of sulfates was that acid rain was destroying our ecosystems. That the burning of fossil fuels, by the way, has a direct health impact on people. Forgetting climate change, just forget climate change altogether. The particulate pollution that comes from burning fossil fuels every year kills millions of people on this planet, on the order of 10 million. I've heard numbers around 5 million, 15 million. It all depends on how you count. So there are a lot of reasons not to be dumping sulfates into the atmosphere, not the least of which is the fact that the pattern of warming that you get from the sulfate effect has other impacts elsewhere on the planet. The atmosphere is connected. And so it's a little bit like the Bugs Bunny lumps that you push something down here, it pops up somewhere else. And so one needs to be extremely careful when one tries to engineer the climate we get. That said, there is a growing effort to look at the potential and the consequences and the science and the ethics and the governance behind what I view as sort of a life raft, a thing that you never want to use, but if things get bad enough, you get on it because the alternative is worse, which is this idea of solar radiation management, where perhaps we reach a point where we realize that civilization is having a hard time. Temperatures are making certain places uninhabitable, et cetera, where we might put aerosols into the stratosphere as a way to buy us time to bring carbon concentrations down. It's an area that is worth, in my opinion, studying, and studying twice, 3 times, 10 times before implementing, of course. But I think it would be really silly to burn a bunch of dirty coal, kill a lot of people as a way to try to mitigate hurricanes in the Atlantic, because you'd make the typhoons pick up in the Pacific. And we haven't talked about typhoons and cyclones in the North Indian Ocean. One of the things that's worth keeping in mind is In the United States, hurricanes are very damaging. There are fatalities, unfortunately, and one would be too many, and typically they're in the tens and hundreds. If you go to the Eastern Hemisphere, so South Asia and East Asia, the fatalities from cyclones can exceed tens of thousands and hundreds of thousands of people, right? Tropical cyclone Nargis in the North Indian Ocean killed over 200,000 people in Myanmar. So, you know, it's a bad trade-off, I think, to try to do that.
We'll go back over here.
Sure. Thank you all for being here with us today. No offense, Professor, but this question is for the two lovely women on the panel. How do you overcome what I assume to be an inevitable fear with what you do? And relatedly, what motivated you to get into this potentially dangerous work in the first place?
You have a good story. It's funny how I got into this career because I was terrified of severe weather, and then I ended up flying to hurricanes, and my grandpa never fails to point that out to me. But I started studying it because I was scared of it, and then I found that there was this pathway that I could take to study it, to let people know how to stay safe. Like, it makes so much sense that I'm at the Hurricane Center now, telling people the forecast and hopefully keeping them safe. And then in terms of, you asked like how I feel about. Are you ever scared? Oh, if I'm ever scared in the storm. No, I think the scariest storm event that I ever had was in Hurricane Sam, and we hit a turbulent bump. And I didn't tell you this, but I'm a mom. I have 2 little kids, and I was a nursing mom at that point. And so I had this cooler with me when we hit this turbulence, and it was the milk that I'd pumped, because you're on the plane for 10 hours, so like, what do you do? And we're strapped in, it's fine, the turbulence is fine, we haven't exceeded the bounds of the plane. So the thing that I was worried about in this turbulence was this cooler that was floating away from me. And thinking, oh my gosh, I have to explain to Todd that he got hit in the head with breast milk, which thankfully didn't happen. But so like my strongest emotion in a hurricane has been like embarrassment.
Thanks.
That's a good story. For me, am I on? I'm so loud anyway, it doesn't even really matter. There it's on. For me, I was always loved math and science. I grew up in South Florida. I went to space camp. I mean, I was really into math and science stuff. And Hurricane Andrew hit. I grew up in West Palm, but we drove by Homestead and saw the damage. And so I was like, how does rain and wind cause that? That is ridiculous. Long story short, went to school, took every science you could possibly take, fell in love with meteorology because it did a little bit of everything, explain why the sky is blue. You have some chemistry in there, you have some physics in there, you got a little bit of all of it, really. Oceanography in there, you get all of it. And so worked my way into the Weather Channel. I can tell you after the whole story. I'm never scared because we have a massive team back at the Weather Channel, and I've been doing this 20 years now, and we don't take risks, like, at all. So some of those clips I was showing you, like, it gets bad, we move in. The second there's debris, I'm out of there, because that can kill you. So we just take a lot of precautions, and it is legit, no joke, safety first. There was one time years ago when I first started the Weather Channel, I was like, I'm gonna set up here. They're like, no, you're not. I'm like, this is where I'm gonna set up. And they're like, no, you're not. Like, you will not be on television if you, like, it's not happening. So I learned very fast that they were like, safety first, and there's no debating it at all.
And I should add too, like, the safety manual that we have for flying into hurricanes is very thick, and we follow it very closely.
Thank you. Also, go
No, thank you.
I have a question. When you look at the Atlantic hurricanes in particular, and you see their track that they generally follow, it looks like they're seated over in the nook of Africa, where I guess the water is warm. I'm curious if one, is that true of storms around the planet, that they're often seated by special geological structures or oceanographic structures? But I wonder also, has anybody ever thought about, could you intervene at those seed points and prevent those storms?
So I think the answer to your first question, are storms generally seeded, is yes, right? So typically you understand them as it's a finite amplitude disturbance that then you have a feedback, the wishy, the wind-induced surface heat exchange feedback, and then the storm kicks off. In a lot of the ones that form in the eastern Atlantic form off of tropical easterly waves. These are undulations of the subtropical jet coming off of Africa that get their energy from the difference in moisture between the wet southern part of West Africa and the arid Sahara and Sahel. And so that gradient gives you these waves, and then eventually every now and again they close off and they form into a hurricane. If you look at different parts of the ocean, the seeding mechanism is different. In some places you have multiple types of seeding mechanisms, like in the Western Pacific, where you can have monsoon troughs and other things but there's always a seed. A question, and I think is a good question, can you interseed before the storm is vigorous and self-sustaining and producing, or at least cycling more energy through it than the U.S. power generating capacity? And possibly, although given that we still don't understand why we have 70 hurricanes on the planet, it could be that there is some regulation, and that if you intercede, all you're doing is creating another storm somewhere. So possibly not.
Yeah, so I have a question that's very much based off of a lay person's understanding of hurricane science. But Professor, you mentioned how rising sea levels contribute to greater hurricane impact by increasing, I guess, increasing the amount of damage produced in storm surges. I'm from Florida, so when I think of rising sea levels, I oftentimes think about how, the ocean is sort of eating up the shorelines. And so I was wondering if in that process, if an increase in, I guess, the ocean's surface area might also contribute to the amount of energy a hurricane is able to draw from the ocean, and the extent to which that produces, I guess, like the inherent damage of the hurricane versus simply the storm surge.
So that's an interesting question. Does increasing the surface area of the ocean increase the energy? And in fact, that's sea level rise is increasing the surface area of the ocean because you're eating land. However, you're increasing the surface area by a very small amount. So the depth of the ocean the typical depth is 2.5 miles, say. And you're increasing sea level by a few feet. So you're only pouring over, the edges are very small. So you're not really increasing the surface of the ocean, the surface area of the ocean very much. But what you're doing is especially if you have an area that has been eroded a lot and it has a very sharp slope to it, maybe waves and surge as they move on shore have a hard time making their way. You lose energy, it breaks. But if sea level rises into a flatter area, then all of a sudden you get less of this breaking in, so the waves can go further in. But the interactions between sea level rise and surge are really complex. And part of the issue that sometimes happens is that you change the shape of the coast. And for example, Hurricane Sandy had a very large surge at the Raritan Bay and the New York Bight because you funneled all that energy in. If you look at the New York Bight, it's a triangle, right? And the Raritan Bay is in there. And you have this huge amount of surge that gets funneled into a tiny little corner. And imagine you changed the shape of some of the bays in Florida, you may get less or more of this funneling effect. And this is a really interesting question that combines geomorphology, oceanography, meteorology. And so, by the way, another thing that you probably should leave with here is just a realization of just how fascinating our environment and the climate and the weather system are. They're really, and having, that was don't downgrade, a layman's understanding of climate. That was a really interesting and pretty probing question. So,
thank you.
Okay, well, I have, sorry. No, I'll only do one more. But Stephanie, you were mentioning that you grew up in South Florida. I actually went to Wellington High School also.
Did you really?
I did, yeah.
Go Wolverines.
Yeah, Wolverines. But I have a question about sort of nomenclature that could go to, I guess, any of you. But when you're looking at hurricanes, right, and they're categorizing them based on wind speed, I assume that's in the eye wall, right? I guess what I'm curious about is that, growing up, I remember actually Andrew, among other things, when they come on land, they often spin off these tornadoes. And tornadoes obviously have substantially higher winds very frequently than whatever's in the eye wall. And I'm curious, I mean, if you're talking about potentially a tornado that's throwing off 200-mile-an-hour winds, maybe for a very limited period of time and in a very limited area, does that count toward anything when you're, just categorizing? And how does that?
They separate the two. I mean, a lot of times, and you can speak more to this, Lisa, is when they come in, the tornadoes are usually in the outer bands that are coming in. Mm-hmm. And those little like metavortices I was trying to point out with Michael coming in within the eye wall? And Lisa can talk way more about those. Those are, in that eye wall, yes, most intense. And I think those are really maybe the spin-ups that people might think of. But they separate, like, Ivan was the most prolific tornado maker, and I'm blanking on the number, 90-something, 109. Do you remember how many tornadoes it had, Ivan, off the top of your head?
I don't, but it was all two in the big outer band as it was coming
in.
ashore. A big tornado outbreak during landfall.
Right, so the intensity is just associated with the maximum sustained wind speed at the surface that's associated with the circulation of the hurricane. So yes, you do get tornadoes. You're typically not going to get tornadoes, too, that are a lot stronger than that maximum wind. Those tornadoes, they're on the order of, E0s, E1s, maybe an E2. So they're going to do some damage. They're going to take roofs off and flip cars and stuff, but it's not going to be like the eye wall of a major hurricane.
And I'll just add, this sounds like a simple thing to measure wind, but when you think about it, it gets complex. When the Hurricane Center says the wind is 100 miles per hour, what they're referring to is a 1-minute sustained wind at a height of 10 meters above the surface of the ground. So there will be gusts, short-lived, that will be much stronger than that, usually on the order of 20 to 30% above whatever the sustained winds are. So they'll often put in their advisories, sustained winds 100 miles per hour, gusts to 120 or something like that. And those, of course, even though they're shorter-lived, they do a lot of damage as well.
There could be a lot of them, too.
Oh, yes.
So so Lisa brought up the variety of observing platforms that they're using. And these observing platforms, particularly the ones that are at the ocean-atmosphere interface, are really important for our physical understanding of tropical cyclones, because the way that the atmosphere and ocean exchange momentum, that is speed and energy and water, are really crucial to setting the maximum winds of a hurricane. And we know kind of how this happens in winds weaker than gale force, but we know that we don't know it underneath a strong cyclone. And in fact, it becomes hard to even define what the surface of the ocean is underneath a big cyclone. The ocean atmosphere interface becomes like an emulsion, where the air is wet and the atmosphere, the ocean is airy.
You could see that in the video. You could see all this foam on the surface, which is pretty incredible.
Yeah, and so defining how high up above the ocean is 10 meters when you don't know where the surface is becomes tough.
Hi, so thank you for answering the question about the coal, and I have a follow-up question to that. India and China are right now the bulk of the coal use globally. India is particularly vulnerable to rains and storms and so forth. I don't know about China because it's not necessarily, I don't know if it's coastal or where the coal is being produced. So I guess my question to you is, do you work with any of the scientists in China or India? And do you think that there is, I don't know how well known what the research is that you do, and if they, I guess my worry is China and India could potentially use this to say, like, hey, we're not going to, we don't want to stop the coal production. It's what's protecting us right now. Because it sounds like from the research, it is very localized.
Yeah, so I think that, again, it's an interesting worry to have, and I think it's really worthwhile. I would say, first off, that, yeah, we work, one of the beautiful things about meteorology and oceanography is how global the community is. In order to do our jobs, we have to share data. In order to do our jobs, we have to share our understanding. And so you have students from all over the world coming to the United States. You have students from the United States going all over the world. We have data sharing back and forth. NOAA should be commended because they have been a pioneer and incredibly committed to open data, just data available to whoever at whatever point in time. It's amazing. So we are a global community. We do share a lot. And the issue with aerosols, sulfates, in the Indian Ocean and in China is relatively complex, even with the impact of those aerosols on cyclones and typhoons. And so even if all you cared about in the world was typhoons and cyclones, it's not clear that burning sulfates or high sulfate coal would help you out much there. Furthermore, you care about more, right? We live in a multi-hazard world, and there is a lot. I mean, when I mentioned the order 10 million people dying from the direct impact of burning fossil fuels, many of those are in South Asia and East Asia. And so there's a direct public health reason locally there to reduce sulfate emissions. And then there's the local impacts on hydrology, drought, on extreme rain, on the winds. So, we live in a very challenging environment. The climate system has been challenging for humanity since we started trying to, be sedentary. And so messing with the climate system only raises a degree of difficulty, and it does it in a way that is not reflected on the score we get, right? So it's not really worth it.
So just to be clear, the scientists that you work with in India and China are not looking at this, or should say, you have not had any hints that this is being politicized in any way?
I think by and large, as scientists, we tend not to politicize things. Sometimes the politicization is thrust on us, but
it's usually thrust on you. I'm not accusing
of
any politicization. No.
No, but I think that there is the question of weather modification is one that has a history in meteorology. It goes back. Wasn't there a quip? I think it might have been Mark Twain. Everybody talks about the weather, but nobody does anything about it. Was it Twain? And so the idea, okay, can we do something about the weather rather than just forecast it and tell people about it? And it's not clear that we have that level of precision in any of the tools.
We'll take the last two questions here.
Hi, thank you. I was curious about the difference between the east and west coasts of Florida, because it has seemed, again, historically, which we've just learned isn't a good thing to look at for this, but that a lot of the hurricanes have happened in the Gulf in the last 20 years or so, at least. Like, my family lives on the east coast of Florida. I'm trying to get them to move off the beach, but they have felt pretty safe because it always seems to be hitting the Gulf. And I've heard that the Atlantic is deeper, and so maybe the hurricanes get slower as they move to shore on the east coast of Florida, but I was just curious of your thoughts on that.
I think in a very simplistic way, once something gets towards the Gulf, you're stuck. Children in the room. Because it can't get out, right? But if you have something coming towards the Atlantic, you can have a front that sweeps and takes it right out. So I don't know if that may be too simplistic of an explanation that you're looking for, but you have a lot more space on the East Coast for the storms to turn away by something, and if it gets into the Gulf, you're gonna have a landfall. And there's all that warm water, and there's some currents in there that we won't get into that can really make these things explode also. So I think that's a super simplistic explanation.
The shape of the shelf, on the underwater shelf,
right,
is different in the West Coast and the East Coast of Florida. However, I think Andrew is a clear example that we should not take the East Coast to be sort of this sort of safe zone, right? That it wasn't the 38 hurricane. also. And the question is how many Cat 5s are too many? And for me and my taste, probably 0 is the right amount. And so, you know, but there are interesting differences between the East Coast and the West Coast of Florida.
Oh, huge.
But I think they're not enough to allow one to say, oh yeah, let's go. I mean, yeah.
Thank you. I would just add, like, historically, yes, they have hit the East Coast as well as the West Coast. So, like Professor Vecchi said, there is no safe space in Florida.
Thank you.
Well, this was very serendipitous. The reason I look like Judy Maxwell from What's Up, Doc, is I was walking out here. I was shopping. I've relocated from Houston. So I'm going to give you a little context, a question, and a confirmation on something that you said. So yes, I'm a Harvey survivor. And it was bad. I was lucky. I did not, I was not in the city when it happened. I was able to stay out because I had some health issues with mold and some other things. So my husband and family had taken care of a lot of issues, but by the time I got in, I ended up having respiratory issues and whatnot, which is one of the reasons I relocated back to Boston. I had been here before. But my question is, it's kind of a multi-layered question. I know from having lived there, you know, you've got the refineries. You have where Houston is situated in the Gulf, and I was looking at your maps up there. You've got the Sahara winds that dump dust in Houston. I believe, and these aren't political issues, they're just facts. Mexico does burn brush fires at a particular time of year, which the winds come into Houston. You've got, did I mention the refineries? The refineries. And then you've got a lot of pollution, and you've got humidity there as well, and very high allergens. So my question is, with regard to climate change, do the refineries, does all of that, did a lot of that, do you think, contribute to how Harvey sat over Houston the way it did and dumped all that rain?
Yeah, so it's a good question. The extent to which refineries or aerosols, because the brush fire, that's black carbon usually that comes out, or whether those modified the circulation to allow Harvey to hang off the coast of Texas for 3 days and just fire hose Houston. It's not clear. We still don't. We can on a day-by-day meteorology, we can say, okay, this ridge over here and this trough over there kept Harvey in place. But my interpretation of the studies so far are that we still don't know whether there was a fundamental cause for that setup or whether it was just one of these bad luck things, right? There's always luck involved in some things. Now, you brought up the issue of mold and the long lingering effects of Harvey. We were having this conversation earlier today. It's easy to see the very punctuated and dramatic effects of a cyclone, a hurricane, when it makes landfall and it impacts a community and people in that moment. But there are also very long-range lingering effects. So your house gets flooded, you lose AC, you're not able to pump the water out, mold grows, right? All of a sudden, that mold is growing there, you can have downstream health effects. In addition, you have heat waves that can follow a cyclone when you lost power. Then you have this challenge of the heat wave-related mortality. You have the psychological trauma. You have the lack of access to healthcare, the lack of access to vaccination. You have the disruption to the infrastructure. And oftentimes we go in and we see the recovery efforts, but we don't actually see the outcome. And there are many places that years after being impacted by a cyclone are still not back to normal, right? Lake Charles is still not. Baton Rouge, after the floods in 2016, is still not. I don't know how Houston is doing.
They do still have some work to do in certain areas, and I will corroborate. Now, this was my experience when I moved here in January. I mean, within weeks, I completely cleared up of all. And this is me. Other people in Houston don't have issues. Some people do, some people don't. But that was me, and I was really glad. I came back to Boston, and I go visit Houston when I can. But the people are wonderful, I will say. It's a great community, and they did an amazing job.
Glad you're feeling better. Glad you found a solution, too, for yourself, that you're better.
Yes, yes, and this was very educational. I can't thank you enough
You're
for
welcome.
doing this. Thank you.
Thank you all.
Thank you. Yeah. And thank you all, of course, for coming and getting educated. I want to thank this terrific space. WBR City Space was great. And for those joining us on the stream, the American Meteorological Society, and of course, none of this tonight would have been possible if it wasn't for the vision and hard work from Anita Godesky. So let's give her a round of applause as well. The good news is that we're not over yet. So everyone is welcome to continue the conversation, continue the education, if you will, and join us for some refreshments and some light fare. Thank you again.